So one of the reasons that prompted me to create this meetup is I used to just run the performance team here, and then I took over the reliability team and a traffic steering and chaos team. And as I was going to conferences, I was talking to other people from LinkedIn, other companies, Google, Pinterest, etc. And it felt like a lot of us are solving the same problems. We're looking at microservice level availability. We're figuring out how to do outlier detection. We're looking at, faster alerting and time to detect. And so it seems like for the problems we're solving, similar in nature, and I feel like at times we're reinventing the wheel, at least maybe we do sometimes on a subset of it. So I wanted to set up a group that we would start to grow in the Bay Area on this topic. And I think the benefit is that site reliability itself is a very large domain. It can encompass monitoring, time to detect, outlier detection. We could even talk about other attributes we have in production like dynamic scaling. I mean, really, as SREs and site reliability, we own a huge domain. It varies by company, but I think the underlying theme is, we keep everything running at the end of the day and make sure that our experience is available to end users. I also think there's value in having this discussion focus on groups, companies, people that focus on sort of web scale type products, right? At Netflix, we've been through a few rounds of trying out various commercial tools. They break, right? We end up building a lot of point solutions where we have maybe billions of metrics we need to distill into a very specific view for our users here to solve a problem. And that doesn't typically exist in a commercial product because you have to get the other 50 or 60 things that come along with it. So I'm not trying to poo-poo commercial products. I think there are some great uses of them, and we have some in-house. But at a web scale for our entire enterprise, I think at Netflix we run globally on Amazon. Actually trying to extract valuable information from that is something that we've been unable to do with commercial tools. And so one of the things I'd like to do with the meetup as well is keep it more purely focused on the way we're solving the problems in our space and try to not, per se, have a lot of vendor presentations, have people come in and talk about their products and what they're trying to sell. I think there are other meetups that do that, and over time maybe we'll have some of that, but initially I'd like to keep that down to a minimum. Looking for feedback on this. If people think there are other topics they want to cover, just email me and set it up and we'll get other people hosting. I was talking to some guys from LinkedIn and they might host one of these, so we'd love to get more people to contribute, and I guess a lot of us have traffic. Your traffic might be a little better, a little more north for people coming down. But so tonight's topic is time to detect, and I put a poll out there, which everybody hopefully saw, might have been a while ago. And in the poll, I put down a set of topics that were of interest to me, and people voted on it, and there weren't any significant outliers in terms of the topics to cover. I think improving time to detect, identify remediate outliers, we're covering those tonight here. System and application tuning, steering global traffic, lowering operational bars, system optimization. So this is just a list to seed the topics, and then if you have others, and especially if you're hosting, feel free to pick anything that you think is key to how you've solved problems in this space. And ideally I polled for other companies to contribute to this as well, and I think as we grow the audience, right now the meetup's about 140 people, but I think when you get in the order of a few hundreds, we'll ideally be able to get more people to participate on a regular basis. And tonight's just Netflix talks. I did try to blend it a little bit, but it didn't happen. So tonight you get to hear from us. So on the topics we have tonight in terms of time to detect, there's really three. The first one is from Brian, who's on the Cloud Operations Response team, and we're going to talk about aspects of our alerting and how we try to get our detection down to more real time. Neeraj, who has built a streaming insight system for us that we consume for some of our alerts and other information. And then Chris Sandin on the real-time analytics team is going to talk about certain aspects of anomaly detection. Okay, so should be good. I think we're going to leave a little time for questions after each one, and then afterwards there's time to browse and eat a few more burritos if you're interested, and then we'll go from there.
Thank you. So I'm Brian. As Coburn said, I work on the response team here at Netflix. He did mention that we're all trying to solve similar problems, so I'm kind of curious, how many people are trying to solve this problem right now, reducing time to detect? Cool. How many of you are actually responsible for receiving the notifications when you have some sort of alert go off? Interesting. Okay, cool. That was just for fun for me. Thanks. So what I thought would be good to go over for our alerting strategy is just to explain in today's world how we look at our signals and which metrics are most important to us and how we kind of think about things here. And then Niraj and Chris can go into a little bit more detail on some of the more technical aspects of how we detect issues. So for me, I was going to go over our KPIs, so our key performance indicators, how we think about those, the data sources, which we've already breezed over, the frequency, which is obviously a huge factor in analyzing a signal over time in a time series fashion, and then the difference, that we look at for static and dynamic threshold alerting. So, without further ado, our key performance indicators are focused around really our main business goal, which is winning moments of truth. Winning moments of truth is talked about throughout Netflix, and it basically speaks to the fact that we're an entertainment company. So we are at odds not only with the people that you may think are obvious, like Hulu and Vudu and other online video offers, but also just other forms of entertainment. Going out to the park, doing this or doing that, just any kind of form of entertainment. What we'd like is when you're looking for a way to go have fun, that you turn on the TV and click on Netflix. So with that in mind, it's our goal in the operations world to think about and figure out what's the most important thing that we can focus on that kind of is in the same realm as this, right? So how do we win moments of truth? Well, you have to make sure the service is reliable. Obviously, you all know that. That's why you're here. So we focus on our customers. 5.5 years ago at Netflix, I started as a customer service agent in Portland, Oregon, and I moved down here a few years back and got involved just a little over a year ago with the operations side. And so I can tell you firsthand that the customers really feel the brunt of things when they're not working. So we focus on the customer, and there's two main kind of interaction points with Netflix that mean the most to us and that we consider our primary key performance indicators. It's probably no surprise that one of them is going to be our sign up. So this is when the customer gives us their credit card and gives us their email address, and we get through the sign up flow and make them give them a free month and hopefully convert them into a paying customer. And the other one, of course, is when you turn on Netflix and you press play, we want it to work every single time. So when we think about this, we have to basically monitor this all day long and find out in different segments how successful are we doing at these things. The secondary indicators that we look at are often indicative of a potential issue that could lead itself to impact our KPIs. So is the website available? Well, other people can sign up for the service through other methods other than just the website, but we still want to know if the website's up and running. Are they able to save their method of payment? So that's one aspect of a sign up, but maybe there's other ways to get through as well. With playback, customers have to, how many people have Netflix? Okay, good. So don't need to tell you this, but when you get on a device, you either punch in your email and password, just like everything else, or our older devices that give you a code and you go into the website and punch it in. Errors are another indication that customers are having trouble, although our key indicator is the ability to press start and it works. Sometimes we'll see spikes and fluctuations in the amount of errors that people are seeing on devices, and that can kind of lead us into trouble as well. So we want to keep a good pulse on those to make sure that people can use our service effectively. So as far as the quality data that I talk about here, it's really just to highlight very briefly the two data sources that we use as a response team, one of which is Atlas. So Chris works on the team that helps build Atlas, and Coburn already mentioned that a lot of the software out there that tries to solve these problems didn't really fit our needs. Atlas is a prime example of a situation where we had to go and build something from the ground up. We needed too much data, and we needed it too fast, and a lot of the offerings out there either could do one or the other, but it couldn't do both. So Atlas is in-house. It's got in-memory storage, so it gets us lots of data, stores it fast, and returns it back to us really quickly. So we get near real-time operational insight from this system, and it monitors, I think, what's the number now, Chris? Like 1.2 billion metrics per day or something like that?
Let's go with that.
Yeah, let's go with that. Sounds great. It's a lot. Mantis is a bit different. Hopefully Niraj will highlight a little bit more of this, but it's more of a real-time event processing system where we can give it ad hoc queries and get real-time insight into what's happening second by second. throughout the system. So both of these come into use for us when we talk about alerting and reducing time to detect. And that leads us into data frequency because this piggybacks on that. So data frequency matters, for a couple reasons. So Atlas you have here on the left. We essentially have the same graphs, just graphed with different granularity. So 1 minute of granularity through Atlas reduces cost of storage of the metrics, so we can keep them for a longer period of time and be able to reference them later. It also, provides us some more confidence. When we see a significant drop like you see here, we have more confidence that that is a real drop that's happened and not something that's just, fly by night and gonna go away very quickly. The 1 second granularity in Mantis allows us for faster evaluation. So the more, the faster the frequency, the more data points you have, and the faster you can make decisions on that data. So I think the thing that I wanted to make sure I don't forget about talking about is that we use a rolling count here. And the rolling count helps give us confidence that, it is worth waking someone up in the middle of the night. That we have a problem. If it drops for maybe a minute and comes right back, maybe, there's 100 different possibilities or more of what could have caused that, but it may not be worth waking someone up. Whereas if you're using Mantis data, it's very likely that you could analyze the data faster and be more confident that you have a significant drop that's worth waking someone up for in a much faster period of time. So static versus dynamic thresholds. So here we have one of our signals. This particular signal is a measurement of our customer's ability to start playback. And what this shows us here is about a week's worth of time. I mean, count the days, 1, 2, 3, about a week's worth of time. And you see the typical pattern of, the morning hump, and then it creeps up, and then right at the peak is kind of around the peak of the day, right? Like for people's viewing. So you have like 4 to 9 o'clock at night, something like that across our major markets. So if you were to design a static line threshold that you're trying to detect a drop, where would you put it? You'd have to put it down below your trough here. So of course, it would go probably somewhere like right there. Is there obviously glaring problems with this? Okay, cool. That's good. So here's why they don't always work. Here's the glaringly obviously problem. So you put a static line right there, and then you have a huge problem that you didn't detect. You didn't detect it because you don't have a dynamic threshold. You don't have something that's actually monitoring your signal for the change that you see variation throughout the day. So what we do currently, and again, Chris and Niraj will talk about some newer methods, but what we do currently is we use double exponential smoothing. So it's a regression model that basically takes that line and takes out the noise and tries to fit a smooth line through the middle of the signal. This one is a very basic DES line. Of course, not of course, but with the DES regression model, you set an evaluation period. So in this case, we've selected 10 minutes. We want to look at the previous 10 minutes. And then we give it a couple other parameters to say what would make this the smoothest line across this signal. But that's not good enough. What's going to happen here is if you leave it right here and this becomes your threshold, you're going to alert all day, every day. So what we have to do is offset that just a little bit. Okay? And now we can use the rolling count that I talked about earlier, where it's to say, if this is our threshold, if we have this blue area, the blue signal cross over our threshold and drop for longer than a certain period of time that you so choose, in this case I think it's 2 out of 5 minutes, then we want it to alert. So it's kind of hard to see here, but that green bar just indicates where the alert actually fired. So the alerting system that we use, also managed by our insights team, sees this. So whenever this type of event occurs, we say normal is 0, there's no alert, nothing's triggered, and then all of a sudden there's an alert. So it hits 1, and now the system knows, okay, I need to act. I need to send out an email and let people know about this, or I need to page people and wake them up in the middle of the night, that sort of thing. So the other possibility, you have a question? Someone? No? Okay. Sorry. The other possibility is kind of when static thresholds and dynamic thresholds meet. And the way that this can happen is through looking at DES, the double exponential smoothing kind of regression model, looking at that as just the residual. What's the difference between DES and your signal itself? So you can see as we're chugging along throughout the day here, we have a very small variation in the difference between them. And then right here where you see an outage occurred, you can tell that there was a huge spike in the difference between DES and the signal. So what that would look like is this. So if you were to graph just the difference between those two lines, you wind up with a line that looks similar to this. And of course, now that we have that dynamic threshold set, we can also lay on top of that a static threshold to say anytime this difference rises above a certain level, go ahead and alert me. So this one has the same rule. 2 out of 5 minutes, go ahead and alert me on this. So the last thing that I wanted to talk about as far as what we're doing today is a standard deviation. So we have if anybody has ever used standard deviation, you're probably aware that it's a fairly naive approach to detecting issues. It works well for us, though, to detect major and significant drops. And the neat thing is we have this model running on our Mantis framework. So here's an example of where we have 1 second granularity on our metric. And the green line is showing the actual threshold that we have set. So the blue line is the average over the course of like 30 minutes. You take all the seconds over 30 minutes, average them out. And then the green line represents 2 standard deviations away from that. And that's how this one's configured. So when we see a significant drop like this, if we were looking at minute level granularity, you would probably be looking at 20 minutes before you find out about the problem. But because this is 1 second granularity, we're able to use the standard deviation method to detect this issue in particular. And I think this one probably went off in around 27 seconds or so from the initial deviation from our norm. So that's how we do things today. And are there any questions? It was rather a short presentation. Yes?
I have a question. Is there a way how you can classify the criticality of this alert? Or they're all the same? Whenever you're generating, it's the same?
So internally, we have a way in our alerting system to set different criticalities. Generally speaking, we would consider them all urgent, but we do have different actions that can be taken. So when an alert fires, you can say, okay, just send me an email. Or you can say, go ahead and alert, we use PagerDuty to alert us in the middle of the night or for our cell phones to ring. So we have the ability to turn those things on and off. And oftentimes if you have like a secondary indicator, I talked about client errors and the website being out, stuff like that, I might rely on more of an email alert for that type of thing. When I'm talking about, you can imagine like PlayStation 3 or PS4, Xbox, these devices are super popular for Netflix. So when we see a huge deviation in one of those, we want to wake up. That's one that we would want all the bells and whistles to go off. Yes?
So the 2 standard deviation approach, assuming that's, you guys are assuming it's Gaussian distribution on that, it
Sure.
doesn't lead to a lot of false positives or?
So far we haven't found that. Niraj may be going to speak a little bit about this, I'm not sure. But it's configurable as to what your threshold may be. So you can say 1 standard deviation or 2 or 3, depending on how normally distributed your data is. And then you can also set a breach count. So it's not the first time that it crosses over your threshold. But you can also, kind of like the rolling count I was talking about before, you can say if 20 out of 30 seconds are bad, or if 20 out of 20, you just want to know consecutive bad seconds. That sort of
But you're not like processing the data to Gaussianize it or anything, right?
Not currently. This guy over here is not doing that on this metric, but we do collect data to smarten the models for sure. Yes, and I'll come back to you.
Do you also have any tools to have it monitor? Do you have like dashboard? Or
Yes.
something like that to have all the alerts?
We do.
You have a team of people looking at it?
Yeah, so we don't have a traditional NOC here at Netflix. So there's no one station that you would go to and see monitors all over the wall and that sort of thing. What we do have is an elaborate set of dashboards that we can reference for checking into these alerts. But I think the idea is, to be efficient and to keep your sanity. You really don't want people just staring at graphs all day long. And honestly, the system is way too complex to be able to monitor everything that would matter. So ideally what we want here at Netflix is we want to create smart alerts such that they don't create so much noise that people become numb to them, but such that people will engage when they go off. And yes.
So with Netflix, for a lot of your stuff, I'm sure it's very high QPS due to a very high sample size.
Mm-hmm.
Do these approaches still work if you, for services inside that get lower QPS?
I want you to save that question for probably that guy, and he's going to hate me for saying that, but
Okay.
save that question for him.
And there's something that's interesting too. We recently cut over using this methodology, and our availability is calculated on the number of streams we miss versus what we should be achieving based on the signal. And in our previous alerts, they were rolling in like maybe every 8 to 9 minutes we'd get something that had violated enough to say, hey, we're having a major problem. And since we aren't watching dashboards, that was like, when you're going at a few 100,000 stream starts a minute, like we actually were able to cut out like half the time. And we actually got one of the issues resolved before the initial alerts rolled in, which was really cool. So the investment paid for itself.
In the one outage? Yeah, I mean, this one that's built on top of Mantis, essentially, if we have a major deviation in a given AWS region, we'll know within a minute. Whereas our old system, like he said, would probably be somewhere with 8 to 10 or even 11 minutes behind.
So I didn't get 1 second for any alert.
Hopefully Niraj will explain that. Is that part of your presentation, Niraj?
Not really, but I can quickly,
Okay.
So we are tracking every single request that comes in, so all the data is streamed as it comes in, so we have access to the fine-grained data.
Yes.
So here you've got, it's pretty obvious when it actually deviates, when it sort of hits that two sigma threshold.
Yes.
Whereas you could just count how many times, it sort of hits either side of the, if all of your new data points are one side of the mean, or some other algorithm like that, you could detect much earlier. So it looks like, when you're just looking at it, it seems like you could detect much more quickly that something strange is happening because it's bouncing either side of the mean pretty rapidly.
That's true.
And going one side of the mean, you've got just a simple filter on this would give you a pretty sensitive thing. You've got, the rate of changing of the filtered data would give it to you.
I wholeheartedly agree with you. I think that the thing that we kind of go back and forth a little bit on is, what do you personally want to wake up in the middle of the night for? Do you want to wake up for a 30-second deviation? Do you want to wake up for a 10-second deviation? Or would you rather it be like 2 minutes? That sort of thing.
I'd like to find and fix something in less than 30 seconds because that's kind of browser timeout. So if you just enable a feature and it blew up the whole site, I'd want to tell 2 seconds later that the site blew up, so you can turn it back off again. So that in that case, you want very short latency, and you want to be able to detect it very quickly.
We probably could easily tune it down to that level.
It could be tuned, absolutely.
It's just sometimes there's so many pushes happening throughout the day, we'll have a hiccup for a minute.
The other thing
goes out, and then it'll.
The other thing too is because we are a substitute for all forms of entertainment. There are events throughout the world that are going to make this signal a little noisy. So of course, huge events like the Super Bowl or something like that might make this go off anyways. But country by country, region by region, there's bound to be noise throughout almost every day of the year. So we try to make it to where, like I said earlier, we try to make it to where we're not creating so much noise that the people watching the alerts become numb. People's attention is very expensive, and we certainly wouldn't want someone to just say, "Oh, this one always comes through. I'm just going to close my laptop and go back to sleep."
Your example, it's kind of highlighting change management more than reacting to systemic blip, right? Like he's got a stasis where things went anomalous, and you're kind of talking about a guy who pushed a feature flag or something. And so maybe, having a dash that's got a 2-second reaction time has that display element in your case, right?
There's use cases for both, for sure.
And it's a lot of difference of opinion. Like on the team that gets these pages, some people want to know in 1 second, and some want to know in 2 minutes. So there's a social part of this.
Yeah, the social side, if I'm being completely transparent here, if I'm at work 9 to 5 and this thing goes off, I want to know immediately. 1 second. Just tell me right now, as soon as it goes bad. If I'm dead asleep at 2 a.m. and we have a 10-second blip, I do not want to know about it.
Brian, we should probably move on in here. I was just
Yep.
questioning, there should be time afterwards.
Yep, we'll get together. We'll have plenty of time. Thank you.
Right, good evening everyone. My name is Neeraj Joshi. I work for the Edge Engineering team. And today I'll be talking about Mantis, a reactive stream processing system that's used to power the next generation of insight tools here at Netflix. So setting up some context. So managing a complex operational environment is hard and Netflix is no exception. We are available across hundreds of countries, across thousands of devices. We have an ever-growing catalog of titles that you can play at any time on any device, anywhere in the world. So in order to operate such a system, you need to develop an understanding of what is going on. Specifically, you need to understand what is working, what is not working, and when something's not working, what is the impact of that. Of course, saying this is easy, implementing this is hard. Netflix has hundreds of software services, microservices that we run, process billions of requests, millions of users, and so on. I mean, it's a combinatorial explosion. We just have too many dimensions to look at all the time to figure out what's really happening. So in this high-tech illustration, I have the relationship between complexity and comprehension. So when things are simple, you just have to look at a few dashboards and you get a good idea of what's really going on. As the complexity increases, so does the number of dashboards that you need to look at increases and gets to a point where you really have no clue what's going on. You just hope for the best. So what we really need to do is shift the curve up so that the comprehension kind of keeps up with the complexity. And to do that, we need to rethink the way we do insights. We need to build new tools that can shift the curve. And this is where Mantis comes in. So what is Mantis? It's a small but extremely fast stream. But more relevant to this discussion, it's a reactive stream processing system. Mantis is used currently, like we have about 75 jobs running in all the 3 AWS regions. Global access to data, we are processing 4.7 million requests per second at peak. We have 20 odd data sources, a lot of generic adapters to gather data from various parts of the system, and we can start up jobs really quickly. Some of the tools that we have built on Mantis, you can roughly categorize them in these categories. So there's long tail analysis where we are looking at everything all the time and trying to do anomaly detection. So for example, we track all the movies in the catalog all the time to detect any deviations, whether a certain title is having trouble getting played. Then there's real-time tracking and alerting that Brian alluded to before. We are looking at key metrics and in real time and doing fast alerting. And then there's ad hoc investigation where you're trying to find a needle in a haystack. You don't really know what to find, but you know something's wrong, and then you can kind of interactively query the system. In the end of my presentation, I'll do a quick demo of one of these. So let me switch gears, talk about Mantis. So let's start with some basic concepts. So what is a stream? A stream is a sequence of events over time. How does Mantis process streams? Using higher order functions. So here we have the higher order function map that takes as input the mathematical function square root and applies it to each element of the incoming stream to generate a new stream. And then a sequence of such functions applied to a stream is essentially a Mantis job. You can group together these functions into one or more stages. The first stage is responsible for sourcing the data. The last stage is responsible for pushing the results out. And finally, each stage can be divided across several workers. So you can scale out based on the volume of data you need to process. So switching gears, some of the key features of Mantis jobs. Jobs can be named. They have job versions. So this allows for jobs to reference each other and source data from each other. jobs are parameterized, so you can build a really generic job and kind of reuse it for different purposes. They have SLAs, so you can set up things like how many instances of the job can be active at a given time, how long a job can run, whether a job is transient or perpetual. And finally, jobs can be chained together to form complex hierarchies of jobs. So this allows the output of one job to be fed as input to another job. So this allows for arbitrary code and data reuse. So this is all fine, but how does Mantis meet the scalable insights challenge? How does it meet the combinatorial explosion that we have to face today? So let's quickly go over some of the key requirements for a system like this. It needs to be cost sensitive, needs to be optimized for low latency, high throughput, and must be resilient. Let's go over these one by one. Minimizing costs. So minimizing costs is very important for an insight system. It is hard to justify an insight system that costs more to operate than the system it is monitoring. Mantis achieves cost efficiency in 3 key ways. First is by using elastic clusters. So the usage patterns of an insight systems are highly unpredictable. When things are running fine, there's low activity, but when something goes wrong, everyone wants to jump in and take a look at the dashboards. So provisioning a system for this occasional peak usage is expensive and wasteful. This is where being cloud native is so powerful. Mantis is able to quickly detect and react to a surge in demand by scaling up the underlying EC2 clusters. And when the demand has subsided, it scales it back down, thus never using more resources that are actually required. The second key way is by using elastic jobs. So the resources required by a job are directly proportional to the amount of data it needs to process. At Netflix, the amount of data varies widely based on the time of the day. So for example, during peak, there's almost 5 times more data than during off-peak. Thus, having a job that's provisioned for this peak usage is expensive. So Mantis supports job auto-scaling. Each stage of the job can be independently configured based on thresholds to scale up and down. So an auto-scaling policy consists of a scaling config where you can set up things like min and max increments and cooldowns between the increments. And you can have one or more strategies where you can set up thresholds of when to scale up, when to scale down, and so on. And the third key cost-saving technique used by Mantis is filtering data at the source. Now in practice, not all the data is required all the time. Many jobs are transient, they come and go. Also jobs that are perpetual are only interested in a subset of the data. So moving all the bits all the time is expensive. So this is where Mantis's deep integration with Netflix comes in handy. Mantis has an expressive SQL-like query syntax that it uses to push the queries all the way up to the data producers so that only the data that's actually required by the jobs is pushed to the system. So this way it is able to optimize on the network usage and save costs. Next, low latency, high throughput. So any system that works at Netflix scale needs to process a large volume of data very quickly. No point in knowing a movie was failing an hour ago, we want to know now. So early in the design of Mantis, we had to make a decision between going with a more traditional blocking thread-based model versus an async model which is non-blocking. And we decided to go with the async model thinking that it will scale better. So recent tests performed by Brendan Gregg, who is with us here. So he's shown exactly that. He compared the performance of RxNetty, which is a networking library based on Netty, which is async, versus Tomcat, which is blocking. And he showed that there are 2 key advantages of using an async system. The first is reduced CPU consumption. So RxNetty consumed less CPU per request. In fact, as the load increased, shown by the blue line, the CPU consumption actually reduced for Netty. And this was primarily because of the event model that Netty uses. It has reduced thread migrations, more cache locality, which basically means that less CPU instructions are executed per request. There's also lower object allocation rate, which basically helps in reduce garbage collection. And the other key benefit is lower latency. So even under high load, Netty shows lower latency. This graph is a little crowded, but the yellow line is the latency line for Netty, and it kind of stays low for a long time. And even when it hits its knee, it is still further ahead of the red line, which kind of takes off quite early. So Mantis is non-blocking not only at the networking level, it is also non-blocking at the processing level. So both the platform and the jobs are written using RxJava, which has a bunch of non-blocking, highly async operators. And the next, resilience. So resilience is very important for an inside system. If your inside system is down, you don't really have a clue of how your actual system is working. And being cloud native has many advantages, but it also comes with the element of instability. So things can go wrong. Servers can fail, hard disk can fail, there could be memory errors, software bugs. In Mantis, however, when a server crashes, any jobs that were running on those servers, they also crash. And so Mantis is designed to be resilient to these kind of failures. It's constantly monitoring the health of all of its nodes using heartbeats. And the moment it detects that a server has died, it's quickly replaced, and any jobs that were running on them are relaunched. The other big source of failures are network issues. All the nodes of Mantis jobs are connected to each other using long-lived stateful connections. So if any of these connections break, the flow of data is interrupted and the jobs fail. So again, in Mantis, each node is responsible for establishing and monitoring its connections. And if any of the connections get terminated, they're immediately reconnected and the flow of data is restored. And finally, back pressure. So any high throughput, low latency system needs to deal with the issues of back pressure. Back pressure basically happens when the processing is unable to keep up with the flow of data. So to build an effective back pressure strategy, you need to understand the nature of your data sources. So the data sources can be roughly divided into two categories. So you have the cold sources like the queues, like Apache Kafka and so on, where the reader can control the rate of flow of data. And then you have the hot sources like server-sent events, which are basically generated after processing each request. And there's no way to slow these down. They just keep coming at you at the pace at which the server is processing requests. So Mantis uses different approaches to deal with different sources. So for cold sources, it relies on RxJava's reactive push-pull mechanism. So in this mechanism, what happens is each operator tells its predecessor of how many elements it can process. And this signal is propagated all the way up to the edge of the network. And then only those many items are read and then pushed down asynchronously. This model is extremely powerful because this allows Mantis to switch from a extremely fast push mode in which the operators essentially request a maximum number of items, and then the data is pushed down as fast as it can be read from the queue, to a slightly slower pull model in which essentially you're requesting a single item and a single item is read and a single item is pushed down. It's almost like a request-response pattern. For hot sources, there's a different strategy. We use what we call strategy functions, which sit at the edge of the network. The back pressure signal flows just as before, except now what the strategy function does is, based on what strategy you've configured, it'll decide whether to drop the excess data, buffer it, or trigger a scale up in the case of Mantis. And then only the appropriate number of items are then pushed down. So in this way, Mantis is able to handle both kinds of data sources, dealing with their different rates of processing as required. So that's a quick breeze through Mantis. There's lots of detail. I didn't want to get into too much technical details. I wanted to leave time for a quick demo that I wanted to show. So one of the tools that we built on top of Mantis is called Mars. So what Mars does is it allows you to do ad hoc querying to find like a needle in a haystack. So say a particular user is having trouble streaming Netflix. So you can go here, you basically have to enter, there's a whole bunch of criteria you can enter, and there's also generic builder, you can pick any criteria you want, and then you can build these queries in real time, and then fire them off, and then this will basically propagate the query all the way up to the edge servers, and it will look at every event passing through the edge servers, and anything that matches the criteria of this particular customer ID, it is going to stream those events down. So hopefully the demo gods will be kind to me. And so I'm just logging into my profile, and I picked the wrong region, of course.
I'm impressed you remembered your customer.
Typing it too many times. All right. There you go. So these are real events that occur when my homepage was requested. And so if you're debugging something, you can set up these queries. You can set up these queries to be persisted in Elasticsearch, for example. You can query from multiple data sources, so you can see how the requests are flowing through all the tiers of your system, like right from the edge all the way to the middle tier, and kind of do ad hoc. Like you can see what's going on, look at the output, then decide, pick a new query, and so on. So
is this AWS or this is?
this is all AWS, yes.
So this cluster auto scales each day from about 200 to 3,000 instances. And so since this is built into it, it's just dynamically sampling across the whole farm based on
Is it going against the database?
No, this is going against the servers directly. So it is connected to the servers, and as the requests are coming into the servers, they are matched against the query.
What's the benefit of this over something like Splunk?
Basically, there's just too much data at Netflix. Like if you try to persist every single event, those tools don't scale. There's no way you can scale it. So what this does is allows you to kind of set up like sharp filters to just get the data you are interested in, and only for the duration you are interested in.
Essentially, this isn't persistent, right? This is just real time and
This
you
is-
do it and it's gone.
Yeah, and you could choose to persist it. Like out here, there's a button called persist, save events to Elasticsearch. So you could run a query and just save those results to Elasticsearch. But yes. Yeah.
Also, example, since we are sort of sampling every request that's coming into the system, are there parts where, I know you had mentioned a filter earlier, where maybe you can do like cardinality estimation, so that you don't have to like keep track of every single data point?
So we do create schemas out of these unstructured events. So we do sample these events to some extent to generate schemas, like what are the different keys we have seen, what are the different values we have seen. So we do that. But for targeted queries where I'm looking for a specific customer, we just get all the data.
You talked about sort of managing a cluster of machines earlier.
Uh-huh.
Are you using an abstract system like Mesos or something like that?
Yeah, exactly.
Okay, so you're starting like Mesos tasks on
Exactly.
just a generic pool, and like you're scaling the actual Mesos pool up and down as you're starting the tasks?
Exactly.
Okay.
More questions? Okay. Thank you, Nira.
Thank you.